All right, so this is homework 5, part C, where I'm going to derive the heat exchange rate for a co-current and concurrent heat exchanger. So first I'm going to draw co-current heat exchanger. That's a tube with a tube inside of it. That has hot liquid flowing on the outside and cold liquid flowing on the inside. That has temperature 1 hot. We'll label these as hot 1 and hot 2, and cold 1 and cold 2. With position, this is position 1, and this is position 2. That has an area of heat exchange, dA. So we're gonna look at the general heat exchange equation, which is Q is equal to U, which is the universal heat transfer coefficient, times the temperature of the hot minus the temperature of the cold, times the heat exchange area. So we would think to just integrate this, but we can't because the temperatures are through that area. So we first have to write the equation as the derivative of the temperature change driving force being equal to the derivative of the temperature hot minus the derivative of the temperature cold temperature. So we know that the mass flow rate times the heat capacity of the hot is equal to the flow rate of the heat capacity, and the same for the cold. And we also know that the MCAT equation from chemistry 1 or chem 2, where so we can write these equations for both the hot and the cold, where derivative of Q, the heat flow, is equal to T, and then we can also write this for delta T, rearrange it for delta T. And we can input these equations into here to get, Well, this first equation, before we get to this, is dq is equal to u delta t dA. So now we can get oh, and this is also negative because the heat flow capacity decreases at minus all right, and now we can input this equation into there, so we get well, first, before we do that, we can take dq out and put it there. So now it's and now we want to separate these in terms of temperature and area. So we're going to write this as 1 over delta T d delta T equal to U and we're going to integrate this. So this will be d2 to delta T1 equal to U times the area. And now we're going to expand this because we also know that Q being equal to negative times delta T is equal to and we can also write for this for the negative or the cold. We're going to input that into there. So So now we're going to simplify again. And solve for Q. And this is the log. The log mean temperature difference. So we could do this for either co-current or countercurrent. So I'm going to show which one's more powerful. So this is position 1 to 2. Where they both start on the one side. And so cold temperature increases and the warm temperature decreases. And so this is the delta T, very small. Driving force is very small. But for countercurrent, delta T, the driving force is very large, so countercurrent is the way to go. Alright, so now we are going to explain the concept of effectiveness and how it can be used in conjunction of NTU. So, effectiveness is equal to Q over Q net. And we just solved for Q. And earlier. And then this can also be set equal to the mass flow rate heat capacity minimum set equal to the mass flow rate heat capacity of the hot times the temperature of heat 1 minus 2 over C minimum times the heat in minus the cold in. And this bottom term is the max heat transfer. And this equation can be used to cool hot flow, or you can write it as mass flow rate of the mass flow rate heat capacity of the cool times the temperature of the heat 2 minus T of heat 1 over the same minimum of the temperature of the heat 1 minus the heat cool 1 to heat cold flow. And now the NTU is the net transfer units and so NTU can be equal to the universal heat transfer constant times the area over the heat capacity, the mass flow rate heat capacity of the minimum so then NTU can also equal F efficiency C minimum divided by C max. So all of these equations can be used in conjunction to solve for the NTU or effectiveness.